In the previous class, we have seen how we can, in the case of combined translation and rotation motion, how we can combine the total angular momentum. We can express total angular momentum into two terms. Okay, first part is angular momentum about the center of mass. Angular momentum due to rotation of the body about the center of mass. This we call spin angular momentum. And second is angular momentum due to translation of the center of mass, that we call orbital angular momentum. Okay, so in the same way, in this case of combined translation and rotation, let us try to calculate the torque on the body. We will see that torque also you can express as a sum of two terms. So let us start with the general definition of the torque. So torque we can write as sum over J Rj cross Fj. Okay. So this is a rigid body. So we take the torque on the jth particle of the body and we sum over all the particles. Okay. Now from the previous class, see, we have this figure. Look at this figure, and from this figure we can deduce that for first particle, one particle, we can say R1. This R1 position vector about the origin of an inertial coordinate system is equal to R plus R1 prime. Okay, in general we can say Rj is equal to, look at equation 3 here, Rj is equal to R plus Rj prime. Okay, so we are going to use this result here. Let us use it here. So instead of Rj, we can substitute Rj prime plus capital R, where Rj prime is the position vector of the jth particle about the center of mass, and capital R is the position vector of the center of mass about the inertial coordinate system. Therefore torque we can re-express as Rj prime plus R cross Fj, where Fj is the total force on the jth particle. So we can express this as sum of two terms. So the first term is Rj prime cross Fj. Okay, plus, now in the second term, capital R, second term is summation over J capital R cross Fj, but capital R is independent of summation. So if you take it outside, what you get is capital R cross summation over J Fj, which is the total force, total external force acting on the body, on the center of mass of the body. Okay, so the total torque is expressed as two terms, and here the first term here, what is this first term? Okay, it is the torque around the center of mass due to various external forces. Torque around the center of mass, or torque about the center of mass, because we are using the position vector Rj prime here. For each particle we are taking the position vector about the center of mass. So this torque, this is the total torque with respect to the center of mass due to various external forces. Fj being all the external, each Fj is an external force on the jth particle, is the total external force on the jth particle, like that. Now what is the second term? The second term is the torque on the center of mass due to the total external force. Torque on the center of mass due to the total, capital F is the total external force acting on the body at its center of mass. Okay, so total external force. So capital F is the total external force acting on the rigid body at its center of mass, and what is the torque on the center of mass? Capital R is the position vector of the center of mass about the inertial origin of the inertial coordinate system. Okay, so this second term gives the torque of the center of mass due to the total external force, right? Torque acting on the center of mass due to the total external force, and the first term gives the torque of the rigid body about the center of mass. Okay. So the total torque acting on the body about the inertial coordinate system we express in terms of torque about the center of mass and torque of the center of mass, okay, or torque on the center of mass. So if you consider only fixed axis rotation, okay, then that means the axis of rotation is along the z direction, then we are calculating the torque about the z axis. Okay, then our expression will be, the first term we can express as tau 0. Okay, tau 0 is the torque around the center of mass due to various external forces, and second term we can simply write this, it is like R cross F z component. Tau 0 is the z component of the torque around the center of mass. Okay, so let us call it equation 1. Now let us connect the expression for angular momentum and torque. We have written expression for angular momentum, the z component of angular momentum, like this in the previous class, I0 omega, right? Angular momentum due to rotation of the rigid body around the center of mass plus R cross mv z component. Okay, angular momentum due to the translation of the center of mass, right? This we have already written, and let us try to connect the two. What is the connection? We know that the z component of the torque, or torque is equal to rate of change of angular momentum, or z component of the torque is equal to rate of change of z component of angular momentum. Okay, so let us try to connect them. Right, so let us equate z component of torque with the derivative of angular momentum. So left hand side is, I am substituting from equation 1, left hand side is tau 0 plus R cross F z component, and right side is derivative of equation 2. So we get I0 times d by dt of omega plus then d by dt of R cross mv z direction. Okay, now in the second term, look at the second term. Right, in the second term, here we have to apply product rule. So when you apply product rule, first derivative of d by dt of R cross mv. Now d by dt of, so first term is d by dt of R cross mv plus R cross m d by dt of v. These are all z component, right? Now in the first term, d by dt of R means velocity of the center of mass, and here v is also velocity of the center of mass. So this is something like v cross v. So this term will be 0. Okay, this term is 0. And the second term we can write as R cross m. The derivative of velocity is acceleration, so ma, right? And this is again we can write as R cross ma is nothing but force acting on the center of mass, R cross z, R cross f z. Now look at the second term on the left hand side, it is R cross f z, right? So these two terms, second term on the left side and second term on the right side, will cancel. So we get the result that the torque of the body around the center of mass is equal to I0 times d by dt of omega is alpha. Okay, so we get an equation like this. Torque around the center of mass is equal to I0 times alpha. Moment of inertia, I0 is the moment of inertia of the body around the center of mass, and alpha is angular acceleration. Okay, this equation is nothing new. This is in translational motion. We know that this equation is equivalent to force is equal to mass into acceleration. Okay, so this is the idea. Basically, equation 1, look at equation 1. The total torque we can write as two terms. Torque around the center of mass due to various external force plus torque on the center of mass due to the total external force. And equating with the rate of change of angular momentum, we get this result. Torque around the center of mass is equal to moment of inertia around the center of about the center of mass times angular acceleration of the body. So we have discussed how the look at equation 1 and 2. First we have established equation 2 in the previous class. The total angular momentum is equal to angular momentum due to rotation of the body around the center of mass, right? And that's the first term, I0 omega, and second term angular momentum due to translation of the center of mass. Okay, so this total angular momentum we can write as two terms, and here we have shown that total torque also can be written as two terms in equation 1. Okay, yes. Now in the same way, kinetic energy also we can express as two terms, translational kinetic energy and rotational kinetic energy. So let us try to express total kinetic energy of the body. So next is kinetic energy. So in these three cases, that is angular momentum, torque and kinetic energy, we are considering combined translation and rotational motion. So we start with this expression, kinetic energy is of the body is sum of the kinetic energy of each individual particle. In order to rewrite this velocity of the jth particle, let us revisit the problem of a drum rolling along a plane. Let us say it is rolling like this along the minus x direction. So let us say this is the jth particle on the body, mj, and the center of mass of the drum is somewhere here. So this is rj prime, position vector about the center of mass, and this is the perpendicular distance from the axis, which is called rho j prime. Okay. So when we look at this rolling of this drum, then jth particle is also undergoing some motion, so it has some velocity vj. Now this velocity we can split up into, this motion of the jth particle we can split up into two parts. One is if this is the z-axis, okay, this jth particle is undergoing a circular motion around the z-axis, okay, with rho j as the radius, rho j prime as the radius. So this is one motion, circular motion about the z-axis, rotational motion about the z-axis. And what is the velocity of that rotational motion? Rho j prime dot. Right? It's a rate of change of this vector about the which is a perpendicular vector from the z-axis. It's undergoing change. So its magnitude is not changing, only its direction is changing. So this rho j prime dot, its magnitude is, we can write it as rho j prime into d theta by dt, or rho j prime into omega. It's a rotation. Okay. And what is the second velocity of this jth particle? If this is the center of mass, this center of mass is undergoing a translational motion along the minus x direction, v. Okay, we have taken this minus x direction to ensure that the angular momentum vector is along the z-axis, plus z-axis. Okay, we can also take it along the plus x direction. So the point is that it is rolling along either minus x direction or plus x direction, so that its angular momentum is along plus z axis or minus z axis. Okay, so this jth particle is undergoing two types of motion. One is rotation about the axis, where then the perpendicular vector from the axis of rotation is changing. Its magnitude remains constant, but its direction is changing. And the second is translation of the center of mass. So the point is this Vj, vector Vj, we can write as rho j prime dot plus capital V. Okay. So we can substitute that value here. So k is equal to summation over j half mj rho j prime dot plus capital V square. Okay. So this is the vector. Square of a vector means dot product of the vector with itself. Then there are three terms here. So first term is half mj rho j prime dot rho j prime dot, which is rho j prime dot square, plus next term is summation over j. We have rho j prime dot product with v plus v dot rho j prime dot. So these are same. So we get twice rho j prime dot plus v. So this 2 and half will cancel. So the second term is mj rho j prime dot product with v. And the last term, there are two terms here actually, and so the two terms are combined. V dot rho j prime dot plus rho j prime dot v is twice the value, and the last term is half mj v dot v is v square. Okay, so in these three terms we can show that this this second term, this rho j prime dot v will be 0. Sum over j rho j prime dot mj rho j prime dot v will be 0. Okay, and how can we show this? Because if you look at this figure, second figure, here the direction of rho j prime dot will be tangential to this circle. Okay, so it will be in the xy plane, right? So if you consider this circle, okay, it will be tangential here. Consider this circle is perpendicular to z axis. This is z axis, right? This axis is z axis. So this circle is in the xy plane. So in this end, it's a vertical circle. So at this end, it will be along plus y direction. Velocity vector of the center of mass is always along minus x direction. So at this end, this rho j prime dot is along plus y direction. At the diametrically opposite end, it will be along minus y direction. So at these 2 points, it's perpendicular to velocity vector. Okay. But if you consider other points, for example, if you consider this point, what I have shown here, it is along the plus minus x direction. So these are in the same direction. Rho j prime dot v is having some positive value, but at the diametrically opposite point here, it is along plus x direction. So rho j prime dot v will be will be in plus x direction, v will be in always in the minus x direction, so the dot product will be negative. So the dot product here and dot product here will cancel when you sum it. In the same way, if you consider two diametrically opposite points, if you consider any other diametrically opposite points, you can resolve rho j prime into parallel component and a perpendicular component with respect to v. Okay, perpendicular component will cancel and the parallel component will cancel with the parallel component from the diametrically opposite point. Okay, that's the idea. So if you consider all the directions of rho j prime dot around this circle, then this dot product will be cancelling out if you consider all possible directions. Okay. Um, so this point, that dot product will be 0. Then it doesn't mean that rho j prime dot is always perpendicular to B. Okay, the different components are it's exactly perpendicular only at this end and this end in this figure. These two ends. One is in plus y direction, other is in minus y direction. But if you consider any two diametrically opposite points, their components will cancel each other. That's the idea. So the remaining terms are kinetic energy equals half sum over j mj, and this rho j dot square, that is rho j dot is, we can write as, look at this expression, this rho j dot is basically it's undergoing this vector is undergoing rotation. Okay, when a vector is undergoing rotation, its magnitude is not changing, only the direction is changing. Then the rate of change of the vector, magnitude of the rate of change of the vector, we can write as the magnitude of the vector into angular velocity omega. Okay, so here this becomes mj rho j prime into omega square, plus second term is 0, the third term is half sum over j mj v square. So this is equal to half sum over j mj rho j prime square into omega plus half sum over j mj. Capital V is independent of the summation, so sum over j mj is total mass of the system, so half mv square. And in the first term, this sum over j mj rho j prime square, remember rho j prime is the perpendicular distance from the axis of rotation, and this quantity sum over j mj rho j prime square is the moment of inertia about the center of mass, right? So because the axis z-axis is passing through the center of mass, therefore we can write this as half I0, there is a square here, omega square, half I0 omega square plus half mv square. This is the expression for the kinetic energy of the body undergoing both translation and rotation. And this first term gives the kinetic energy due to the rotation of the body around the axis passing through the center of mass, and the second term gives the kinetic energy due to the translation of the center of mass. Okay, so that is the meaning. This first term represents kinetic energy of rotation around the axis passing through center of mass, and the second term is kinetic energy of translation of center of mass of the body. Okay, so these three equations, equation 2 about angular momentum around the z-axis. This is expressed as two terms: angular momentum of rotation of the body around the center of mass plus angular momentum due to the translation of the center of mass. Torque acting on the body along the z direction is torque due to motion of the body around the center of mass due to external forces, and second, torque on the center of mass due to the total external forces. And so we have expressed angular momentum as sum of two terms, torque as sum of two terms, and now kinetic energy as sum of two terms. So in each case, one term is due to the rotation around the center of mass, or rotation around the axis passing through the center of mass, and the second term is corresponding to the translation of the center of mass.